Hey folks, time to get down and dirty. Linear algebra is a very applied subject, and one of the things we're going to do throughout this course is write some things in a programming language using an environment like R or Python in order to demonstrate the concepts and show some of the computational power, and also to do a few applications. So this is where the class is going to sort of break into two tracks, as it were. I'm going to do R in this section, which I believe is segment 9A of episode 2. And then in segment 9B, I will do the Python equivalent of this. You only need to do one track. You can do both if you're interested in learning both languages. Otherwise, you can choose the one that your instructor has chosen for you or that you are most interested in learning. Both R and Python are extremely widely used in many, many situations by many organizations and companies throughout the world. I'm personally an R guy, but I know some of my colleagues at the University of Mary Washington are more Python people, and I respect them and their choice very much too. Both languages can get the job done. It's sort of unfortunate that there are as many languages as there are, especially because there's so much overlap in what they're able to do. But that being said, if you want to do the Python track of this course, you can stop watching this video now and just jump ahead to segment 9B. If you're going to do the R track, then that's fine. You can do this now, and then you are done with episode 2 when you are finished with this and don't even need to move on to 9B at all. So they are completely mutually exclusive in that sense. And now, we're going to learn how to do a lot of these basic vector operations in R. R is a programming language and a statistical environment. Your instructor has given you instructions on how to set up R, and that may differ from what I'm showing you here on the screen in terms of the environment and in terms of the exact tool set you use and how everything looks and is laid out on the screen. All the important stuff is the same though. Once you get down to typing stuff in R in the window using the programming language and the syntax of the R language, it's all the same. It doesn't matter what any of the little buttons say or which quadrant of the screen your output shows up in or anything like that. So I'm going to be using Rstudio, which is a very popular integrated development environment for R. It's point and clicky and it's nice because you can see your variables and organize your plots and stuff like that. To be honest, I don't use that in my everyday work. I just use a plain old text editor called Vim. And run R that way, but I'm doing it this way for this course because I think it's more common for people these days to use a point-and-click environment. Feel free to use Rstudio. It's free, just like R is and always will be. But there's other point-and-click environments as well. There's R Commander and several others, so do feel free to use the one that's right for you. So I'm going to, with each one of the R lessons of this volume, I'm going to provide a cheat sheet, and here is this one for this course, or for this episode rather. Lot of different things here that I'm going to sort of run through. Most of this is simply so you find it easy to remember and refer to. A lot of these things are going to be very difficult to understand just reading the cheat sheet, so I do recommend that you follow along here. Feel free to have your own Rstudio or R language up and be typing in commands and experimenting with those as we go, or simply watch. It's up to you. Rstudio looks like this. And what we're going to be doing over here is on the left-hand side of the screen. We're not going to be doing anything with the right side of the screen right now. Left side of the screen up here is where you put your R program by typing things. One of the first things I'm going to type is a comment line. So in R, if you prefix a line of code with a hashtag, then whatever you say is basically ignored by R itself, and it's only there for human consumption. So I'll say, getting our feet wet. And we'll say Stephen and friends. There. This is not going to be interpreted by R, thank God, since this is not valid R syntax. But any line that you put with a hashtag is ignored by it, which is useful not only for commenting your program by saying what it is and how it works and stuff. It's also very useful because there are times when you have a bunch of code that isn't working and you want to temporarily disable part of it. And the way you can do that is by prefixing each of the lines with a hashtag, which sort of temporarily takes it out of commission and makes R ignore it for the time being. All right. So first thing we're going to do here, and I'm not really going to refer to the cheat sheet. I'm going to post this so that you can look at it at your leisure. But in R, as with all programming languages, there's the notion of a variable. And it's very important. We can make a variable called anything we like as long as it's basically a string of letters. So we're going to make one called x here. And one of the fundamental things in R, and this is how you create a vector, is you first of all use this little arrow to say I'm going to assign this new vector that I'm making into the variable x. If you've done programming before, this is very, very natural to you, and you've seen this a lot. If this is your first experience with programming, just note that variables in a computer program are just like variables in math, really. When we say, let x be the vector 5, 4, 7, that's exactly what I'm doing here. I'm saying set a vector to the name x that has certain values. And in R, the way we make a vector with 4, 6, and 7 in it is we use the C command, and we say 4, 6, 7. You can think of that as meaning create. Actually, it means concatenate or combine, but that's not important. You just need to know that you can say C. And if we do that and then we run our program by pressing source here, then down here I could say X and hit enter, and it'll show me the value of X, which is 4, 6, and 7. You can ignore this part for now, this thing where it says boxy, 1 boxy. That's basically telling you that the beginning of the vector, element number 1 of the vector, is number 4, which isn't terribly useful right now, but if we have a really long vector that stretches all the way across the screen, it's handy because it can show us what each subsequent line is numbered at. But for now, you can just ignore the boxy, 1 boxy and just look at the rest of the elements here. And I can go up here and I can make a Y, and I can say set that equal to 5, 5, 5. Here's something that may come as a surprise if you haven't done programming before. If I say x gets 1, 2, 3, I have now overridden the previous value of x, because when I run this program by pressing the source button, all of these lines get executed in order. And therefore, this line assigns the vector 4, 6, 7 to x, and then this line does something to y, and then this line says, oh, JK, just erase the previous value of x and replace it with this new value. So if I run this thing again and then say, hey, what's x? It says 1, 2, 3. The old value 4, 6, 7 is obliterated. So that's not something we see in math a lot. Usually we say if there's a variable that has a certain value, it always has that value. It doesn't change as we read the page or whatever. But in programming, that's extremely common for variables to change values often as the program progresses. Okay? R allows you to do very basic operations as well as complex ones, but I can do simple things like vector addition. So we could say, hey, what is x plus y? And I can do that in 2 ways. If I just come down here and interactively type x plus y, it's going to compute the vector addition for me, and you'll see that it did the vector addition right, because here's x and here's y, right? So if we add those together element by element, just like we do in a vector addition, we get 6, 7, 8. No surprise. The other thing we could do up here is put x plus y, but in order to get it to actually show up here, we're going to have to say print banana, x plus y banana. And that's our way of saying, hey, R, when you run this program, not only do I want you to set these things to these values, but I actually want you to print to the screen as a side effect the value of this thing right here. And so if I run this, it says 6, 7, 8 to the screen because it ran that print command. Okay? We can do things like subtract. I could say, hey, what's x minus y? And if I run that, it prints 6, 7, 8 because that was from line 9 up here. And then it prints -4, -3, -2 because that's the value of x minus y. I can even do x times y. So I'll replace the x minus y with this time. And you will see that it gives me 5, 10, 15, which is precisely what I told you isn't a mathematical concept, right? If we say x and y, x times y in the dot product sense doesn't give us a vector, it gives us a scalar, right? And so you may be surprised when I did this x times y and it actually did the multiplication element by element and gave us another vector. That's simply because it's sort of a nice convenient shorthand in terms of programming. There are times when you sort of conveniently want to multiply each element of a vector times the corresponding element in a different vector. Much more common, of course, to do the dot product, and the way you do that in R is a little bit strange. What we're going to do is we're going to say x percent splat percent y. And the way you do that is you just say there's a times, but putting the parentheses around it, or excuse me, the percents around it is R's way, for whatever reason, of saying I want you to actually do the dot product thing. And so if we do that, we're going to get back 30. Again, ignore this, if you will, and ignore this, if you will. Those are simply orienting us to what could possibly be a larger solution. But for right now, we just want to say, we're just looking at the value right there, and the dot product of those two vectors together is 30. Here's something that's a little odd. If I want to do exponentiation, it's not that odd, I guess. So here's x, right? If I say x squared then what I'm going to get is this. It squares each element of the vector. This little caret sign is how I do a to the power of, right? I could even say, hey, what's x to the 8th power? And I get something really big for the third element here because 3 to the 8th power is evidently that thing right there. We can also say square root. If I say, hey, what's the square root of x? It's going to say, well, that's 1, 1.414, which is the square root of 2, and 1.73, yada, yada, which is the square root of 3. So that's another little function here. Notice there's a lot of things we do in R that have these bananas and then some stuff inside the bananas. This thing inside the banana is called an argument or a parameter. And what that means is, really, we're saying, hey, I want to invoke the square root command, or I want to, the way a programmer would say this is, I want to call the square root function, and I want to pass it the argument x. Okay, so that's kind of a mouthful, but I'm going to be using those words a lot, so you want to familiarize yourself with that terminology. What I'm doing here, again, is I'm calling the square root function. We'll learn how to write our own functions later, actually. Right now I'm using one that's out of the box that kind of comes with R. I am calling the square root function, and I am passing it, which means giving it, the argument x. I could also just say, hey, what's the square root of 16? And it would tell me 4. Or what's the square root of 18? And it would give me that big thing, right? So I don't have to actually have a named variable that I give to the square root function. I can just say, hey, here's a particular value. Or I can say, hey, what's the square root of the vector 4, 5, 9? And it's going to say 2, 2 point something, and 3. So here I have made a vector on the fly and given it to the square root function without naming it. And that is totally permissible. And of course I can do that up here too. I can say print what is the square root of the vector 4, 5, 9, and if I run this puppy, it will again print us this value here after it did the other things that I told it to print. All right. Let's go to a few other things here. So one way I can make a vector that has a bunch of different things in it, or I should say a bunch of elements that are the same in it. Let's say I want to make a vector of 100 zeros. I can say 0, 0, 0, 0, 0, and type that 100 times, but of course that's no fun, and computers are good at doing automated tasks. So what I can use is the rep function, and I can say rep the number 0 100 times. And if I do that, boom, I get back this huge vector with all these things in it. And this is where you might notice where this little boxy comes in handy. This is telling me that the first element of this big long row is starting with element number 1, and then just so I can get my bearings here, it's telling me that when I go to the next row, it's starting at number 68. And if I did this with 1,000, I would be able to see, where all of them were, where each row started. And with all zeros, it kind of doesn't matter a lot, but if I have some data actually here, that will help a lot. By the way, one handy thing in Rstudio, just in case you're using that, if you press the up arrow, it cycles back through your previous commands and allows you to edit them and re-execute them. So that's how I did that rep 1000 so fast. I went up to get it, and then I changed it. So now maybe I'll say, hey, I want 1,013s, or 12s, I guess I pressed. I'll change it to 13. I like 13 better. And then it made 13 of those, right? Which, of course, is very different than saying I want 13 1,000s, which would be just that thing right there. Another thing in R we'll do a lot is we'll create vectors that are in a sequence. So if I say, hey, I want the vector 3, 9, it gives me a vector from 3 to 9 by 1s. If I say 3 to 109, it gives me that whole vector there. If I say, hey, I'd like 103 to 347, please, it gives me that whole vector right there. So that's a really easy, quick, snappy way to create a vector that has a bunch of elements that go in a certain pattern like that, right? Another thing I can do, sometimes I may want to go from 1 to 100, but I want to go by 5s, or I want to go by 2s, or I want to go by something other than 1s. To do that, I use the seek function, that stands for sequence. And what I can do is I can say I want to go from 1 to 100 by 2s. And if I do that, you can see it goes 1, 3, 5, all the way up to 99. Notice it didn't make it all the way to 100 because that didn't work out evenly. If I said I want to go from 1 to 100 by 3s, it would go all the way up and land on 100 because starting with 1, adding 3 each time, you get up to 100 evenly, right? I could also go backwards if I want. I can say, hey, let's go from 10 down to -5 by -3s. Oops. 10 to negative 5 by negative 3s, and that will count backwards like that. So those turn out to be come in handy sometimes. I can also do random numbers. R can do a lot of very, very, very sophisticated random number things. Just to show you a extremely simple one, there's a function called runif, and that stands for random number according to the uniform distribution, which you may have learned about in a stats class or may learn about in a future stats class. All that means for us is it's saying it wants a number between 0 and 1. So if I say I'd like 5 of those, please, it gives me a vector with 5 numbers, each of which is a random number between 0 and 1. And if I say I'd like 50 of those, it does that. And so you might say, well, what if I want a random number between 0 and 100? Well, all you have to do is say, run this thing, and then multiply by 100, right? And then it's going to take each one of those random numbers and scale it up by a factor of 100, and that effectively gives you one in the 0 to 100 range. I could also say if I want integers, I can do that whole thing and then truncate the result. So if I do that, now it's rounding down. So truncate, if I give it a vector like 4.5 and 4.3 and 4.8, it's going to truncate all of those down to 4. Okay, that's different than saying round. If I round, then it's actually going to round the 4.8 up. And the other two, it's going to round down to 4. So if I did the truncate, it's always truncating down. So if I wanted to roll some dice, let's say I wanted to play Yahtzee, I can say, let's roll 5 dice and multiply that by 6. Now, if I do that, I'm getting 5 numbers that are between 0 and 6. So if I take those numbers and I truncate them, I'm actually going to be between 0 and 5 for my answer, right? And I don't know about you, but I've never seen a die with a 0 on it. So really what we need to do is add 1 to the answer there. And I'm going to get back now a vector that has 5 dice. So every time I roll this, it's like rolling 5 Yahtzee dice. Fun stuff. Okay, a few other things here. If I have a vector like x and I say, hey, what's the length of x? It's going to tell me 3 because it just tells me how many elements are in there. What's the length of the vector that goes from 103 up to 347? Oh, that has 245 elements, sir. What's the length of if I go from 103 to 347, but I go by 15s? Oops, forgot a banana. That's only 17, it tells me. So that's kind of a handy thing. I can also extract elements from a vector. So if I have x like this, and I say, hey, I would like, actually, let's use y. Well, let's see. Let's make a new vector. In fact, let's do the die roll thing, right? So if I do my little die roll here, I could set that equal to x by doing this thing. So now x is my die roll. If I want to say, hey, what's number 2 of that die roll? It gives me 6 because 6 was element number 2 of the die roll. And if I say, what's x of 4? It tells me 2. If I say, what's x of 5? It tells me 6. If I say, what's x of 2 through 5? It tells me 6, 5, 2, 6. Because when I say x of 2 through 5, that's basically saying, give me elements 2 through 5 of that vector. I could also say, what's elements 1 through 3? And that's 4, 6, 5 of x. Or I could say, what is elements 3, 1, and 3 in that order? And that's going to give me 5, 4, and 5 because element number 3 was a 5, element number 1 was a 4, and element number 3 again was a 5. So R makes it very easy to sort of mix and match these vectors. Right here we're using a vector to index into this other vector, right? It's kind of tricky. We're giving it a vector of numbers which we want it to use as the index numbers of x so that it gives us the values of x that we have specified. All right, fun stuff. Okay, let's just do our basic operations here. So that's x and this is y, right? So we know how to do a scalar times a vector, and that's just going to multiply each element of the vector times the scalar. Scalar times a vector multiplies each of the elements of the vector times the scalar. We know how to do vector addition, right? So if I say x plus y, that's not going to work right now. It's going to give us a warning. It's going to say, whoa, 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 whoa. Your objects are of different length here, dude. Are you really wanting to add a vector of length 5 to a vector of length 3? And I'm going to say, oh, silly me, of course not. So maybe I make a different vector and I say, let's make that 1 through 5. So now it's the same length as x, and now I can meaningfully say x plus z. And also, if I say, hey, what's x dot producted with y, it's going to say, whoa, 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 can't do that, non-conformable arguments. Whereas if I say x dot product with z, it's all fine because x and z are the same length, as we talked about before. Just a couple more things. In order to figure out the norm of a vector, it's a little bit awkward, so it'd be nice if you could say norm x. Unfortunately, you get a message like that that says it doesn't work, and there's some technical reasons behind that. Basically, what you have to do is say norm matrix of x. Now, matrix is going to be a big word for us in the next episode. Right now, I haven't even defined what that is. For now, just sort of memorize that when you do a norm, you have to tell it not only, in other words, instead of giving it the vector you want it to take the norm of, you have to say matrix of that vector, and that's just sort of a technicality there. The other thing you have to do is tell it which kind of norm you want, right? We mentioned that there are many different kinds. If I do type equals 2, and yeah, you have to put the 2's in quotation marks there, that is going to do the Euclidean norm, right? 10.8166. And we could verify that that's actually the right answer by saying, hey, let's take 4 squared plus 6 squared plus 5 squared plus 2 squared plus 6 squared. Let's add all those up, and then let's divide by, then let's take the square root of that. And we get 10.81665, right? So this norm, where we said a type 2 norm, was really just a nice convenient shorthand for doing this thing for us, right? We can also say, well, maybe I don't want the type 2 norm, maybe I want the type 1 norm, which you remember is simply the sum of the elements there. By the way, there's a slick way to do that in R. You can just say sum of x, and it will take the sum of the elements right there, right? So we could have actually done this, get this, sum of x squared, and then take the square root of that. What do you think of them apples? Okay, so that ends up giving us precisely the Euclidean norm. The same thing we got from running the norm command up here. So you might ask, why would we run the norm command when we can just do it this way? The basic answer is you can do it either way, and so that's fine to do it that way. Norm has some extra features and does some error checking, and also is maybe a little bit faster for large vectors, but in principle, that's all the norm is defined to be, and so you can do it that way. We can also say, give me the 0 norm, which you'll remember doesn't like that. Why doesn't it like that? I guess you have to say O instead of 0. It's kind of odd, but that's what you have to do. So now we're getting the, no, that's not right. All right, I take it back. It's not doing what I thought it was going to do the type 0 norm, which was the sum, or excuse me, the number of non-zero elements, right? So I guess you can't do that with the norm function, which actually I'm glad that happened because this gives me an opportunity to show another thing here, right? So if I wanted to say x of 3 through 4, right? That basically says, give me elements number 3 and number 4 of the x vector. I can also do something like this. Check this out. X, where x is greater than 3. Now that looks really weird, but what it's basically saying is, please give me not a specific numbered indexes, but please give me any values that satisfy this formula here. So that gives me 4, 6, 5, 6, because those are the ones that are greater than 3. 2 is not greater than 3, right? If I say x where x is less than 5, it gives me 4 and 2. If I say x where x is less than 0, it gives me that, which essentially means no elements in it. It's saying there's 0 numerics that satisfy that particular thing, right? So one of the things I could do here is I could say, give me the sum of x equals 0. That tells me how many elements in the vector are equal to 0, and it says there's none of them. How many are equal to the number 6? There's 2 of them. How many are equal to the number 4? There's 1 of them. So what I can do, if you want to find out the the 0 norm of a vector, is I could say how many elements are not equal to 0. Now, that's a really weird way of writing it, but that's how almost all programming languages write it, actually. We call this bang equals. It's an exclamation point equals, and that just means not equals. You'd sort of think they would do it like this or something, I don't know. But there isn't a readily available equal sign with a cross through it on the keyboard, and so we substitute this thing here. So if I do that, that's telling me there are 5 elements of x that are not 0, and therefore that is the 0 norm of the vector. All right. And then finally, let's do the infinity vector, right? And you remember that the infinity vector is simply the maximum value of it, the maximum absolute value, and that turned out to be the 6 in this case, right? By the way, another way to get the max of a vector is you can say max x, and you can say min x, and those give you the maximum and minimum of the vector elements accordingly. Okay, so far this data has been pretty contrived, right? We've been just making up an x and a y and putting just sort of random values in there. Let's make it a little bit more real by going back to this matchmaker example we did. So you remember that I said that Jezebel, if we don't normalize the vectors, would be able to cheat at the matchmaker.com scenario, right? Because she could just say, well, I'm going to answer 10 to all the survey questions saying, yes, I love this, I love this, I love this. And then she's bound to get a higher score when paired with any guy than somebody else who's taken the survey seriously would, right? So let's look at what that's going to look like in Rstudio. So let's go up here and say, let's make a vector called Jezebel. And we'll say, you know, she answers the questions 10, 10, 10, 10, 10, 10. Let's say there's 6 questions. And we're going to say that Cindy, who is actually taking the survey seriously, answers the questions quite differently. She says 4, 4, 9, 3, 0, 8. Okay, so she obviously, for whatever question number 3 and question number 6 on the survey was, she ranked them quite high, but it's not like she was just, you know, babbling optimistic stuff all the time. She actually took the time to show the survey, you know, what she actually thought about various activities and stuff. All right, so let's make some guys. Let's make Biff. And let's say Biff is 5, 6, 7, 6, 5, 4. Okay, and let's make a Pete. And we'll make Pete be 1, 2, 3, 4, 5, 6, 7, or 1. I'm sorry, just through 6. And then let's make it Filbert. And we're going to make Filbert be 4, 4, 9, 3, 1, 9. Okay, so not exactly the same as Cindy, but pretty darn close. In fact, they're identical in the first 4 answers, and then the last 2 they only differed a little bit, right? All right, so let's source this here. Now, and it's still printing the stuff that we had before. Actually, let me get rid of that, just so our screen isn't cluttered. All right, source that thing here. And so now we can look at them. You know, here's Jezebel, and here's Cindy, and whatever. All right. So here's the thing, right? So if I say, what's Jezebel, and I say, let's do the dot product of her with Biff, I get 330. Whereas if I said, well, what is Cindy with Biff? It's only 157. So according to that measure, Jezebel is a lot better match for Biff than Cindy is, right? Which may or may not be true, but here's what's certainly not true. This is going to say Jezebel and Filbert are a 300, whereas Cindy and Filbert are only a 194, right? So this is going to pair Jezebel with Filbert instead of Cindy with Filbert. In fact, it's going to pair Jezebel with anybody compared to Cindy with anybody, simply because Jezebel has such high scores, right? Okay, so the way we get around that, again, is we're going to say all these vectors we're going to normalize. And the way we do that, again, is we take the vector and we divide it by its norm. So let's do the type 2 norm, because that's kind of the standard Euclidean distance thing here, right? Again, if you have not, I'm sorry, I didn't mean X. Let me say Jezebel. If you have not done programming before, you know, just realize that what we're doing is taking the value of Jezebel and dividing it by something, and then setting the value of Jezebel to be that new thing, right? So it's a little bit weird. It's kind of like this. If I say x gets 5, and then I say x gets x plus 1, now x has 6, right? So I used the previous value of x in a computation which then set a new value of x. And that's what I'm doing here. I'm using Jezebel twice, actually. Once to get Jezebel herself and one to compute her norm in order to compute the new value of Jezebel, which is going to be the normalized Jezebel, right? And so let's run this, and then let's say, hey, what's Jezebel look like now? And you can see it has set all of her values to 0.408. And really, there's some great intuition to get here that you want to make sure you get, right? What we've done is we've said, Jezebel is really pointing equally in all 6 directions. So we're not going to give her any, extra special powers just by putting a bunch of 10s here. What we are going to do is we're going to make it so that she is equal in all directions. But of course, if we say, what is the norm of Jezebel now? It's 1, because the norm of a normalized vector is 1, duh. And in fact, if we had somebody else here, let's say we had Patty, and let's say Patty was 1, 1, 1, 1, 1, 1, right? She hated all the survey questions or whatever. So let's normalize Patty as well. And I don't actually know a good way to do this besides copy paste. When I'm in Vim, which is my editor of choice, I could do this super fast with some advanced editing operations, but that wasn't too bad. All right, so I'll look at Patty, and Patty's just like that, right? So Patty and Jezebel are remarkably the same once they are normalized, and that's because they are both perfectly balanced across all the questions. All right, so let's normalize everybody here. Normalize Cindy, Biff, Pete, Filbert. The girls together and the guys together, just because then I can feel like I have some sanity here. Cindy, Cindy, Cindy. And then these are going to be Biff, Biff, Biff. And then let's get Pete, and this is going to be Pete equals Pete divided by Pete's norm. And then we're going to get Filbert, and we're going to say Filbert gets Filbert divided by Filbert's norm. Great, so we run that thing, and now they're all together like that, right? Now, let's take Jezebel and dot product her with Filbert. We're going to get 0.857. Whereas if I dot product Cindy with Filbert, I get 0.9959, right? So Cindy and Filbert are way, way closer, and that's how it should be, because they have answered the questions in the spirit in which they were given. But this is, let's reduce this to a math thing. This isn't just a social networking thing, right? The fact of the matter is that Cindy and Filbert are pointing in the same direction more in that 6-dimensional space, because they both have very long directions on survey questions number 3 and 6, and they have an extremely short direction, 0, for Cindy and 1 for Filbert in survey question number 5. And they're similar in the other ones as well, right? It's not to beat this to death, but the point is that they're more similar in terms of what they're high on, what they're low on, and doing the normalized vectors is what's going to handle that. Okay, one last thing, and then I will say goodbye for this episode and catch you on the next one, is that very, very often when we're working with data, we are getting that data from a file rather than from an R program, right? We're certainly not going to type in all the data that we want to use. So what we need is a way to load information from a file, and there is, of course, a way to do that. So I made this file here. This is what our temperatures in Fredericksburg have been lately. These have been our daily high temperatures. So 3 weeks or so ago, it was 79, then 75, then 80, then 84, and you can sort of see the pattern here, right? So this is just a plain old file. Don't mistake this for like an Rstudio file or anything like that. I'm just loading this in Rstudio, but I could easily have also shown it in Vim or Microsoft Notepad or WordPad or in my web browser. It's just a plain old text file with just a bunch of numbers in it. And the way you load that in R is you use the scan function, and you have to give it the file name. Now, this is the only tricky part. A lot of people these days, I've discovered, don't really know how their file system is organized on their hard drive or on their computer. So I know how mine is, and so I happen to know that this file here, Fredericksburg, is in the directory or in the folder Home Stephen Teaching 125. And then I'm going to say fredericksburg.txt. And then I'm going to assign that to a variable. I'm saying, let's call that weather or something like that, right? And it says read 22 items, and if I type weather, then lo and behold, I have gotten a vector of those items. And I can say, hey, what was the lowest high temperature for the week? Okay, and what was the highest high temperature for the week? And what was the average high temperature for the week? I could say sum of weather divided by length of weather, right? And I get the average. I could also say mean of weather. But just to show you that we can build up all these things from the little components that we have. So what I was going to mention about that is that this part is hard for people, I've noticed. If you're running like Windows, what you may have to put here for the scan is something on the order of C:\\documents and settings / something. This is where you have to kind of go into your file explorer or whatever it's called on Windows and figure out exactly what directory your file is in. And it's pretty error prone because you have to type it exactly right, and you have to make sure you have the right drive letter and you have all the directories in the right order and all that kind of stuff. It's just one thing I've noticed. It's harder for people than it ought to be these days. They just still haven't managed to make computers quite as easy as they ought to in some of these simple concepts. But at any rate, when you do a homework assignment or want to play with some data that you found on the web or something like that, you'll need to know how to scan it in. And really the hardest part about that is simply knowing how to specify what the file name is. And that's how you do that. So, thank you for tuning in to episode 2 of volume 2 of All the Math. I will catch you next time, and we will pick up talking about linear independence.